join us from the waiting room. If you'd like to, please feel free to go ahead and add your name and your school affiliation in the chat if you'd like to meet some other MBAs. Welcome. We are about to start Climate Science for MBAs. I am Katie Cross. I am the co-founder of ClimateCAP, and I'm also an educator in the sustainability program at Duke University's Fuqua School of Business. So for any of you who are incoming Duke MBAs, I look forward to meeting you very soon on campus. And for those of you who are students at other schools, I hope to meet you at the ClimateCAP MBA Summit in February, which hopefully is already on your calendars. We are so glad that you have joined us today for our session on climate science for MBAs. I know that you read the headlines. I know that you've taken your environmental science classes before, but this is a field that's always changing, and we always start Climate Catalyst with the climate science. For those of you who want to get really grounded in the facts and the statistics and the trends before we get into the discussion of the business implications and the career opportunities later in our program. So we are delighted to have Drew Isaacs here, who I'll introduce in just a minute. If you haven't already gathered this from our Climate Catalyst program, one of the terrific things about this workshop is you get a chance to hear from terrific professors at other business schools. So you are sitting wherever you are, but we have in our program professors and educators from a number of different schools on the agenda for you in the next 2 days. So a couple of notes as we get started. Again, please feel free to introduce yourself in the chat if you'd like to meet other students from other schools. As we go through the presentation, we'll ask you to use the Q&A button for questions. And then after Drew is done presenting, I will moderate questions with him. I am also joined on the call today by Jessica Wingard, who's our ClimateCAP program lead, and she will be helping to monitor questions from the Q&A and also notes in the chat as we go. We like to start each of our ClimateCAP sessions highlighting one specific feature of ClimateCAP. So if you joined us for the previous session, you already had a chance to hear about everything about ClimateCAP does. Our goal is to educate all of you, today's MBA students, about the business implications of climate change and help you connect with inspiration and the resources you need in order to become climate change makers. If you missed the previous discussion, we hope you'll check out that recording and visit our website, join our newsletter. I will highlight just one of our programs for you today, and that is the summit that I mentioned a moment ago. So our MBA Summit, every year, it's our flagship event. It brings together over 400 MBA students from around the world to network in person about climate in business. We have terrific speakers, we have career sessions, we have inspiration, we have hands-on workshops and skill building sessions. And our next summit will be in 2027 in February at the Fordham Gabelli School in New York City. So it should be a great time. It's a lot of fun. It sells out super quickly. So mark your calendars now, plan to attend, and I hope to see you there. Also, just a quick thank you to our sponsors who have made Climate Catalyst possible: Deriva Energy, Apex Clean Energy, and Environ. And now the reason you are all here today is to hear from Drew Isaacs, who is a senior lecturer at UC Berkeley's Haas School of Business. We have shared Drew's full bio on the registration page, so you can read it there. He has a long list of accolades. In the interest of time, I'm just going to turn it over to Drew right now so that we can jump into our content. But I hope you'll have a chance to learn more about Drew and his work, connect with him, and ask questions as we go.
Thank you, Katie. I'm going to go ahead and share my screen, and I'll ask you to confirm that I have successfully done so. You should be looking at a picture of the Earth.
Yes.
Is that right?
Yes. Looks good.
Okay. And I just advanced my slide, and it says part 0. Is that right?
Yes.
Okay. So welcome, everybody. It is great to see you. My name is Andrew Isaacs. I teach at the Haas School of Business at UC Berkeley. I teach the course called Climate Change and Business Strategy, which I launched 20 years ago. And I guess it's had some traction ever since. I'm delighted that you're here today to join in a very mini version of that course. I am a scientist by training. I started at NASA. at the Johnson Space Center in Houston before working in Silicon Valley and then being recruited to come to Berkeley many years ago. Now, the course that I teach at Berkeley is 15 weeks long. This session is going to be about 37 minutes long. And so we might leave out a few details, but you can think of it as a primer on some of the more important elements of what goes into climate science or what climate science is. And that may help your thinking as you think about solutions and what the implications are for business. So let's go ahead and get started. Here's part zero. Part zero is a reminder that climate change, how can I put this? You may not be interested in climate change, but climate change is interested in you. These are the first two big smoke events that occurred in the United States that were clearly amplified by climate change. New York City and, in fact, the Midwest and much of the East Coast of the US and all of the province of Ontario and other parts of Canada had one of these events just last week. It's just tapering off now. But the first one 3 years ago in New York obviously made the news, actually in a bigger way than the one that just happened made the news. 3 years prior to that in San Francisco, we had a very similar smoke event. These are wildfire related events. And what I'd like to point out is that the significance of this is that these smoke events are not caused specifically by climate change. They are amplified by climate change. Really important distinction. We won't dwell on it, but there's a whole field of climate science that's emerged in the past 10 years to try to figure out how much amplification of these kinds of climate events are is attributable, how much the amplification is the result of climate change. And the reason I'm starting with this is because it's a tap on the shoulder for everyone, not just folks like you who are climate aware, but your parents, your friends, people who may not be paying attention to this at all. It's a reminder that this is very much here with us. In case you need another reminder of why this is happening, it's because the Earth is hotter now. This is a temperature map showing Canada's increased temperatures over the past few decades. And Canada, on average, is heated up about 2 degrees Celsius. That's about 4 degrees Fahrenheit from where it was, say, in about 1960 or so. Now, the result of warming the planet is that air can hold more moisture. And so, if air can hold more moisture when it's warmer, and it can, then you'll tend to dry out the land more. And that is precisely why Canada's suddenly, it seems, having massive forest fires because the forests and the forest fuel, things that can burn in a forest, are much drier now than they were a few decades ago. So will these smoke events continue? Oh, yeah, for sure, because there's nothing that's cooling the planet right now. And as you already know, we're actively warming the planet. Now, part of this picture is also in the news these days, which is that there's yet another war that, although it's not necessarily about oil, is related to oil. And the price spikes that you've seen recently in crude oil and in distillates like gasoline and jet fuel and so on are indeed related to the fact that much of the economy is globally is still dependent on fossil fuels. It won't be going forward, but it is today. And I want to quote probably the most prominent climate scientist in the US today, Andrew Dessler. He's a professor at Texas A&M. But I'm just quoting him directly here and pointing out that, it's worth pausing to appreciate what fossil fuels made possible. They powered our civilization for the last 200 years. But the transition to renewable energy isn't a rejection of that legacy. It's the next chapter, and it's a better one. And since you're all business people, I'll also point out it's cheaper. For the first time ever, renewable energy is less expensive than conventional fossil fuel sources of energy. We're not done with fossil fuels, but that transition as we'll see at the end of my talk, is very much underway, more than you would normally get just by reading popular media. Okay, part one, climate science itself. Where do we get data about the climate? Well, all of the data I'm about to show you about what's happening in terms of climate change is extremely well sourced with highly redundant monitoring systems. Worldwide, there's about 21,000 weather stations in operation. They report on a continuous basis. But typically, what you'll have is every 5 minutes or every 30 minutes or every hour, those weather stations will report what they're observing in terms of temperature and humidity and barometric pressure and other things. That results in about 200,000 measurements on Earth's land surface every month. So that's where we get our data from. It's unlikely, even if one weather station is gone offline or is broken in some way, it doesn't really matter. And it's unlikely that this would be skewed or even skewable in any particular way. So we have so much data. The third bullet point points out that for the 70% of the Earth that's ocean, we actually have better data than we do on land because we have fully automated systems, some of which are moored, but most of which float. And so we get tremendous amounts of information about sea surface temperatures of the air immediately above the ocean surface, and of course, temperature profiles of the ocean down to a mile and a half depth or so. So we have tremendous amount of information, and it allows us to produce images that look like this. This is a color-coded map of the Earth for the year 2025, and the colors indicate how much temperature at each location on the Earth has changed relative to the mid 20th century. This is typical of how climate data works. We take a recent period of time, the full year 2025, with many millions of temperature measurements around the planet, and we compare those for averaging for 2025 to a 30-year average, which you can see in the lower left-hand corner, the years 1951 through 1980. And the color key at the bottom simply indicates how many degrees Celsius of temperature change there's been from that mid 20th century average through to 2025. Now, when you look at this, after you sort of ponder it for a minute or so, you start to realize that there's patterns here. One pattern is that the higher latitudes, higher northern latitudes in particular, have had more temperature change than, say, at the equator. Why is that? Well, that's because high northern latitudes used to be covered with snow and ice for much of the year. But since the Earth already started warming, beginning in the 1950s or 60s or so, the snow cover at high latitudes sticks around less and less and less. It melts earlier in the spring, it forms later in the fall. And the result of that loss of snow and ice cover is that the dark ground or dark Arctic Ocean is exposed and absorbs heat from the sun better than snow and ice do, which are white and reflects the sunlight, reflects the sun's light back into space. So that effect is called Arctic amplification. We've been predicting it for decades. We now observe it actually every single month as these data are published monthly, but it's very clear in this image as well. The second thing that you'll notice is generally the land is heating up faster than the oceans. That's also an effect that we understand completely. It is the result of the fact that oceans have two tricks for pushing heat downward. One is they're made of water, and water is very conductive of heat, and so heat gets conducted downward away from the surface, tending to keep the ocean's surface relatively cool, even though they're absorbing a lot of heat, the surface stays cooler. And the second trick is that oceans, again being made of water, mix. And so there's currents and tides and wave action that tends to mix hotter sea surface water to depth, and that also has the effect of keeping the air above the oceans a little bit cooler. The land has neither of those two tricks, And so the land surface, the continents, are heating up faster. That's incredibly bad news. It's incredibly bad news because it's not just people that live on land. It's most life on Earth is on land. There's life in the oceans, but most species, the mass of life, the variety of life, it's mostly on land. And that's the part that we're preferentially heating. You'll see some other interesting artifacts if you look closely at India. The Indian subcontinent is not heating up as fast as the rest of Asia. That is the result of the Indian subcontinent, India, Pakistan in particular, burning a lot of coal for producing electricity. And that coal puts a lot of ash into the air, and ash reflects sunlight back into space, sort of like an umbrella would. And it keeps the subcontinent a little bit cooler. That's also not good news. So if India transitions to India and Pakistan transition to renewable energy, solar panels and the like, there'll be less soot going into the air, and India will heat up as fast as the rest of Asia is. So there's many other patterns here we don't have time to go into, but the takeaway point is we absolutely know what's happening in the climate to the Earth's climate. It's not that we're confused about it, or that there's one thermometer somewhere that we're measuring data with. By the way, you'll be getting these slides, and in the lower right-hand corner of each slide is the source for everything I'm showing you. Okay, here's another way to look at global warming. We have records, instrumental records going back to January of 1850. So it's about 175 years of instrumental temperature records. And the year is shown from January to December along the lower axis. The vertical axis is how much the temperature has warmed relative to a kind of a pre-industrial average, 1850 to 1900. And the three most recent years are shown in black, red, and what looks like orange up at the top of the images, the top of this image. And you can see that the past 3 years have been the hottest that we've recorded. Not every single month, but generally month by month, the trend is clear. And you can certainly see from the layer cake coloring of this graphic that the 1800s were cooler than, say, 1900 to 1950, and so on. You can also see that the lines, the colorful lines, are farther and farther apart as time goes by, because the temperature increase of Earth has been accelerating. And so the gap between lines is getting bigger. At this point, I'll also pause for just a second and remind you that if you have questions or thoughts, please put them into the chat. We are saving 10 or 15 minutes at the end here for discussing them. Katie is kindly facilitating the whole process, so please put your questions into chat as they come up. Okay, so why is this happening? Why is Earth heating up? We know that it is heating up. Um, and it's clearly related to the concentration of what we call greenhouse gases. The most important of them is CO2, carbon dioxide. CO2 is responsible for about 2/3 of global warming. Um, and it is the highest that it's been in at least 2 million years. I'm being very conservative when I say 2 million years, because it's more like 5 million years, maybe more. And we have geologic data that show us this. So we know what the CO2 in the atmosphere was going back millions of years. And so we are able to say that now we have not had this concentration of CO2 in the atmosphere in at least 2 million years, and more likely, more like 5. Now, two other greenhouse gases are mentioned here too: methane and nitrous oxide, that's CH4 and N2O, shown here. They're the highest in nearly a million years. Again, we have geologic data that help us understand what these atmospheric concentrations were in the geologic past. So we're pretty confident of that. So if CO2 is about, let's call it 65% roughly of climate forcing, Methane is about another, oh, 15 to 20%, nitrous oxide, maybe 3 to 5%. And then there's some other gases as well. But these three are the main actors. The additions of CO2, methane, and nitrous oxide to Earth's atmosphere as a result of industrial practices like driving cars and flying airplanes and heating our homes with natural gas and many other things that involve um, producing these gases. That's why they're increasing in the atmosphere. And we know that from isotopic data. I won't go into the details of that in the interest of time, but there's no question about where these gases are coming from. It's not volcanoes, it's not magic. All right. Um, it's also true that the last 10 years include all 10 of the warmest years we've ever recorded. In fact, the last 3 years are the three warmest years recorded. When I give this talk, I hope 1 year from now, I'll just up those by one. We'll be able to say that the last 4 years are the four warmest years that we've ever recorded because 2026 is coming in about where 2025 was in terms of being a very warm year. Now, let's move on to part two, which is probably the core of the climate science in this very brief talk. So there are these things called greenhouse gases. We're going to look into what these things are, and we're going to take just a very brief journey from Fourier to Keeling to Vostok, Fourier and Keeling, kind of bookend our understanding from beginning to recently what greenhouse gases are. Vostok is a place. So here we go. Um, I put the Earth and the Moon together on the slide. They're not actually this close right now, but you can see their relative sizes. The moon, as moons go, the Earth's moon is very big. As planets go, Earth itself is very small. Uh, they're not entirely different in size. The moon is smaller than the Earth, but not by a heck of a lot. And yet, the moon is small enough that it can't hold an atmosphere at all. It's why it looks like rock, because that's all that it is. There's no atmosphere on the moon. The Earth, slightly larger, is barely big enough to have an atmosphere. Barely big enough. And only for heavier gases, light gases like hydrogen and helium, escape off into space. The Earth is just too small a planet to hold them, very light gases. So we do have an atmosphere on the planet, but it's very thin. And if you were to look at the planet at the Earth's atmosphere edge on, that's the left-hand picture here, that's the whole atmosphere. It's that thin blue line. Um, you know that the atmosphere is thin. If you've ever climbed a mountain, you're climbing up through the atmosphere very quickly. It gets thinner fast. So there's not much mass to Earth's atmosphere. What that means is that if we burn enough fossil fuel, where the fossil fuel was taken out of the ground, it was in solid or liquid or gas form, but it was in the ground, sequestered away for millions of years. If we take that coal, oil, and natural gas out of the ground, set fire to it, and release the combustion gases, CO2 in particular, into the atmosphere, we'll change the composition of the atmosphere. And we are. So here's what Earth's atmosphere looks like in terms of its chemical composition. Nitrogen is the main one. Oxygen, which should be your favorite element, about 21%, a little bit of argon. And the balance, just a fraction of a percent, those trace gases include various greenhouse gases. And that's what we're adding to by burning fossil fuels. Now, those top three gases at the top are transparent, both in the visible range that your eyes can see and also in the infrared range, meaning heat. Your eyes can't see infrared light, but it's very much there. It's what you call heat, or you experience as heat. That's infrared radiation. Um, those three gases at top, they're transparent to both infrared and visible light. The, the other gases, the trace gases, are transparent and visible. You can see through them, but they trap infrared light. They trap heat. And it's the physics of why the planet is warming, because as we add to gases that trap heat in the atmosphere, we are going to warm up the planet. And then many, many, many things follow from that warming. Um, the metaphor that's used is to say putting greenhouse gases into the atmosphere is like adding a blanket to the planet. The physics of how blankets work is actually different from how greenhouse gases work. But as a metaphor, it works. When we drive to the Safeway and burn gasoline doing so, that CO2 stays in the atmosphere more or less indefinitely. And it acts as a blanket that little by little warms the planet. And of course, if hundreds of millions of people drive cars and fly airplanes on a daily basis, then the effect is much larger. Now, the potency of these different greenhouse gases varies. And again, you'll have these slides. You can study this if you want. But as you look down the left-hand side, you'll see various chemical names. In the middle, you'll see the chemical formulae. And on the right-hand side, you'll see a stack of numbers. Carbon dioxide is given a global warming potential of 1. And then we ratio the potency, meaning heat trapping ability of each of the other gases. We ratio that to CO2. So you can see methane is about 25 times more potent molecule for molecule than is CO2. Nitrous oxide, about 300 times more potent molecule for molecule than is CO2. And some of these, like sulfur hexafluoride, are thousands of times more potent. Um, all of those, or most of those gases that have fluorine in them, which is most of the rest of them on the list, are refrigeration gases. And that's the connection between refrigeration gases and climate change. So as I mentioned, it's the burning of fossil fuels, coal, oil, and natural gas, that's taking carbon out of the ground and putting it in the air in the form of CO2 that is about 2/3 of climate forcing. And this very nice chart from the International Energy Agency tracks global energy related CO2 emissions and how much they change over since 1900. There's a typo there. This is actually since the year 1900, not 1990. Um, so you can see that in 1900, we were not burning much coal, oil, and natural gas. We were putting maybe 2 or 3 gigatons of CO2 into the atmosphere. Now we're closer to 40. Um, and although Earth's population has gone up by a factor of about 4, from 2 billion people to 8 billion people, the emissions have gone up substantially faster. You'll see a downtick there in the year 2020. That is COVID. You'll see other upticks and downticks. But the main story here is that it's more or less monotonic, or at least it has been monotonic since about 1950 through to the present. And I just stuck a red line here, not as a regression curve, but just to point out that the increase has been more or less linear. Um, Now, who figured out that there was a connection between the atmosphere, the concentration of these greenhouse gases in the atmosphere, and temperature change? And it was actually more than 200 years ago that a French mathematician named Joseph Fourier proposed that there must be a connection between the chemical makeup of Earth's atmosphere and the temperature of the planet. Otherwise, Earth would be much colder. We're very far away from the sun. The sun is not a particularly bright star. And so it must be that there's something about our atmosphere that's causing this. And 3 years later, a French chemist did a little bit of math and said, yep, it's probably CO2 and water vapor in the atmosphere. And that's why the Earth isn't freezing cold all the time. 30 years later, an American chemist named Eunice Newton Foote was the first to show in experiments and publish that if carbon dioxide levels were higher, the planet would be warmer. So it's over 150 years ago that this was first done in experiments. A couple years later, they were repeated by another scientist named John Tyndall. Same experiments done in a European laboratory. And 30 years after that, a giant of a chemist, Svante Arrhenius, won the Nobel Prize in part for his work using modern chemistry to show that if we burned enough fossil fuels, coal, oil, and natural gas, we could actually warm the planet. And so the science was pretty well wrapped up, at least in terms of predicting what could happen regarding climate change, well over 100 years ago. In the 1950s and 60s, a scientist at UC San Diego named Charles David Keeling, this person, started to record the composition of CO2, the concentration of CO2 in the atmosphere on a continuous basis, making measurements every hour. And that turned out to be a major watershed event. He did his work in San Diego, realized he was too close to a city to actually measure hourly results because he was measuring things like rush hour, which throw off the data. Moved his lab to Hawaii to get away from the congestion of California, but it wasn't this Hawaii, it was this Hawaii. He wanted to put his lab on top of one of the giant volcanoes on the big island of Hawaii. And the reason was you're halfway up through the atmosphere and you're kind of in the middle of nowhere. You're in the middle of the Pacific Ocean, so you're not going to get data influenced by a nearby city. Here's what the lab looks like. It's still there, still recording data. It's the Mauna Loa Observatory on top of that volcano. And I downloaded last night the most recent data from that observatory, and here they are. This is the CO2 concentration in the atmosphere over the past week, ending today. It's kind of a little bit of a down, uh, jaggy line, I guess, but that's a week of data. Let's go back a month. Here's a month of data, meaning from today going back in time 1 month to the middle of June. And you can see there's a slight downward trend in CO2 concentration from maybe 431 parts per million or something like that to maybe 425 or something. Anyways, a slight downward trend. And if we look at 6 months from today, looking back in time, 6 months, you can see that actually there's sort of a dome-shaped distribution. The CO2 is rising and then falling a little bit. Hard to make sense out of just 6 months. Here's 1 year. Now it looks vaguely like a sine wave. You can see CO2 falls during some months and rises during others. And all that effect is whether or not it's summer or winter. During the summer months in the northern hemisphere, plants grow, and plants take CO2 out of the atmosphere, as you know. That's how they make a living. They take CO2 out of the atmosphere and make plant tissue out of that CO2. And so during the summer months, CO2 in Earth's atmosphere actually falls. And the rest of the year, it rises as leaves fall off trees and decay, as grasses die. All of that biodegradation, natural microbial degradation of plant material, puts the CO2 right back into the atmosphere. So you see this kind of wave function. Here's 2 years. Now there's something new that you can observe. Not only is there that kind of sine wave, sawtooth pattern to it, but you'll also notice that the highs are getting higher and the lows are getting higher. That's us. That is human beings adding CO2 to the atmosphere, on top of which the Earth's biosphere is doing its natural growing and dying cycle. If I show you the whole pattern, going back to 1958 when Keeling started this work, that's what's going on. That rise from about 315 parts per million to about 430 parts per million, that's us. That's roughly 50% increase in CO2 in Earth's atmosphere since pre-industrial times. In the pre-industrial era, let's call it 1850 or so, CO2 was at about 270 to 280 parts per million. So it had risen a little bit before Keeling started recording this in 1958, but it's risen dramatically in these last 70 years or so. Now, I also want to point out that that curve is a curve. It's not a straight line. And you'll remember that earlier we were looking at the increase in addition of fossil CO2 to the atmosphere, and it was a straight line. It was a few minutes ago. I put a red line up against fossil CO2 going into the atmosphere. It's a straight line. But the accumulation has to be a integral function of that. If you took calculus, you recognize what's going on here. If I'm adding something faster and faster and faster and faster and faster, the accumulation is going to be an exponential curve. And that's exactly what the Keeling curve is. It's an exponential, it's not a straight line, because we're still adding CO2 faster and faster than we were in the past. Now, if the burning of fossil fuels and the other contributing causes of CO2 winding up in the atmosphere were to level off, the Keeling curve wouldn't go down, it would just go horizontal. The only way to get the Keeling curve to go down is to reduce or eliminate the burning of fossil fuels. Um, that's how you get it to go down. Otherwise, if we just level off our use of fossil fuels, CO2 in the atmosphere doesn't go down. It just rises at a steady rate, no longer an exponential. Okay. Um, we can go back farther in time. I will include these slides in my presentation so you can see what they look like. This is going back to the year 1700, concentration of CO2 in the atmosphere. Here we are going back to the year zero. Here we are going back 10,000 years. So you can see that for the entire sweep of the development of human civilization, say 10,000 years ago, right through to the present, there's been no change in Earth's atmospheric CO2 until maybe the last 75, 100 years or so. It's the burning of fossil fuels that's causing this. And I can go all the way back to 800,000 years ago, and you can see the zigzags now. These are the ice ages that Earth went through, warmer, colder, and so on. This is probably a good time to mention that as CO2 goes up in the atmosphere, the planet gets warmer. It must. CO2 were it to go down in the atmosphere, the planet will get cooler. It must, and it does. There's plenty of understanding of this. And the swings, if you're looking at the ice ages as you are now, the swing between the high peaks, which is hot, and the low valleys, which is the cold, this would be the glacial expansions, it's about 6 degrees Celsius. Okay. And if you look at the right-hand area where my cursor is making a circle right now, you can see that the Keeling curve is a complete excursion from the climate of the ice ages. And in fact, that's if this vertical sweep is 6 degrees, then what's this? It's not 1.5 degrees, like the Paris Agreement says. It's quite a bit more. Okay. Where's all the CO2 coming from? It's coming from something that looks like this. The top equation is the burning of methane. You produce CO2 and water. The bottom equation is my proxy for gasoline, which is I'm using octane there, C8. That's the compound that everybody knows the name of because it's how you price gasoline. But gasoline is a mixture of hydrocarbons. All hydrocarbons look kind of the same. It's just the ratio of how many carbons to how many hydrogens changes from one to the next. However, when you burn them, you get the same thing. You get water and CO2. So all these reactions look like this. And again, reactions just like this, combustion reactions, the burning of coal, oil, natural gas, you wind up with the exact same two waste gases resulting from that combustion, and that's CO2 and water. Okay, part three. I can add in the other the contributions coming from those other greenhouse gases. And here I've cumed them up. So the from 1990 through 2023 in this particular chart, this is from the UN Environmental Program. The dark black part of the curve is fossil CO2, meaning coal, oil, and natural gas burning. Those emissions have been rising pretty steadily. But the next one up is methane on top of that. The blue is nitrous oxide, and then a thin layer for those fluorinated gases, and then another layer in green, which is essentially land use changes and deforestation and reforestation. and how much those are contributing to um, greenhouse gas emissions. And the term that we're using here, you can see in the upper right-hand corner, is gigatons of CO2 E. E means equivalent, and it's a method that we use that's fairly straightforward to make it look like all gases behave like CO2 so that we can compare them to each other side by side. So we say this is how methane would be adding to climate change if it were as if it were as potent as CO2, meaning more weakly potent. Now, there's some good news and some bad news in this. One, the bad news obviously is it's growing because emissions are growing. Um, the good news, such as it is that all of the greenhouse gases, other than CO2, have half-lives. They break down in the atmosphere. Those fluorinated gases break down pretty quickly. Nitrous oxide has a half-life of about 100 years. Methane has a half-life of about 10 years, so a fairly quick, rapid breakdown. The problem is we're adding methane and nitrous oxide faster than they're breaking down. And that's why they're accumulating in the atmosphere. But it's also the reason why, if you were to cut back on methane emissions, you would quickly see the impact from that. Now, CO2 does not have a half-life. It doesn't break down. It goes away in extremely slow geological processes that take tens of thousands to hundreds of thousands to millions of years to occur. So CO2 is really forever. It cycles in and out of the oceans and plant life, but it doesn't go back into the earth unless we were to capture it and put it there. Okay, in a couple of minutes, we're going to go to the Q&A, but I'll share a few more things with you. Quite obviously, there's more in the slide deck that you'll be getting than we're able to cover in this short talk, but hopefully you'll page through and enjoy it. I think we'll close on this. This is a NASA data set. There are 5 or 6 gold standard climate agencies, 2 in the United States, 2 in Europe, 1 in Japan, and China has one that's emerging as a very good standard. It's relatively new, but these are independent climate agencies collecting data independently of each other, and that allows us to see if we're getting concurrence in terms of different data sets. Here's NASA's data set. This is just showing temperature from the 1880s through 1900, relatively constant rather. The blue dot is the global average temperature, land and ocean combined, for those 20 years. If I add the next 40 years, there was actually a little cooling trend you can see from about 1900 to 1910, a little bit of a warming trend after that. 1940 is where it gets interesting. Global temperature shifted up just a little bit, about 0.2 of a degree Celsius. And you can see that there were no more cool years. There were warmer years, but it was looking kind of horizontal. There wasn't much of a warming trend until about 1980, and that's when things clearly changed. And we started to realize that actually that trend could probably be traced back farther than 1980. But by 2000, it was clear that we were seeing warming. This is temperatures now. The 2010s to about 2020, that trend continued. Your eye at this point wants to draw a straight line through this. Human brains want to draw straight lines through things. If you did, that would be a mistake because the next few years gapped up a little bit. This is a phenomenon we've been observing now for maybe 15, 20 years. We'll see a gap up in temperature and then it stays up, does not revert to where it was. There's 2022. Here's 2023, almost off the charts. 2024 is off the charts. And 2025 is maybe about the same. The current year, 2026, also about the same. This no longer looks like a straight line. This starts to look like a curve. And because it's happening in real time, we're now modeling maybe our climate projections, which were kind of straight line projections about the future, more or less, making assumptions about human behavior, were probably not accurate. Let's see. We'll close with this slide And then, Katie, I will turn the floor back over to you. Um, this is the question I get most often, which is, how's this year going to be? And the answer is about the same as last year in terms of temperature. These are predictions through about 6 weeks ago, done by Berkeley Earth, which is an NGO here in Berkeley. And you can see that the likely range, which is shown in green, is about the same as the past few years. The red is how we're doing so far through May of this year. Like I said, through about 6 weeks ago or so. And so we're tracking in a new kind of regime. Um, 2027 is likely to be a record year. And the reason for that is because an El Nino is forming now in the equatorial Pacific, which is a climate and oceanographic event that happens every few years in which the ocean releases a lot of that stored up heat into the atmosphere. And you wind up with global temperatures taking a jump up. And that's one of the reasons we're seeing these gap up kinds of events happening. Okay, I'm going to go ahead and stop sharing my screen and we'll take the last, let's see, 10 or 15 minutes for some Q&A. Katie, over to you.
Thank you, Drew. That was amazing. And really great to have so much data, so many sources to follow up with. We have a number of questions. Some of them are clarifying and some of them are more philosophical. So we'll see what we can get through. Just though you've given us like a really compelling set of data about rising CO2 levels and other greenhouse gas emissions, as well as the rising heat. Can you take the next step further? I know it could be its own lecture, but give us, 2 minutes on what are the actual impacts of climate besides just rising global temperature?
This is like torture telling me to do this
I,
in two
I know,
minutes.
I know, but a snapshot for those who aren't necessarily connecting all the dots to weather and wildfire
Sure.
smoke and things.
When you heat up a planet, many things change. Um, the ecosystems in particular are quite sensitive to change. So that's not just the food that you eat, but it's ecosystems that have nothing to do with you, forests and coral reefs and that sort of thing. So there's the what you should expect to see is changes in ecosystems that are especially temperature sensitive. And one of those happens to be coral reefs, which is about where about a quarter of life is in the oceans, is associated with coral reefs. They're very rich ecosystems. And that's why they're dying. Another effect of increasing CO2 in the atmosphere is that it doesn't all stay in the atmosphere. Some of it dissolves, about a quarter of it dissolves into the oceans. And when you dissolve CO2 into water, you get an acid called carbonic acid. If you've ever had Coca-Cola or beer or any other carbonated beverage, you have experienced carbonic acid. It's a mild acid, but it's what gives you the little bit of bite that comes with a newly opened Coke, as opposed to a Coke that Coca-Cola has been open for an hour. The CO2 is gone. So that's the effect of carbonic acid. You've experienced it. Well, we've been dissolving CO2 into the oceans. Um, we, the Earth does this automatically. As CO2 increases in the atmosphere, it must dissolve into the oceans, and it does. And so the oceans are about 30% more acidic now, meaning the pH has dropped. They're more acidic now than they were in 1950 by about 30%. That's really bad for anything that lives in the oceans, like fish. Um, Other effects are the fact that we are melting permafrost in the Arctic. About a quarter of Earth's surface is permafrost. It's not a rare animal. And as we melt the permafrost, all of the organic material in the frozen soil starts to, what's the word? Starts to degrade and form methane, which is a greenhouse gas. And so that's something that you would call a positive feedback loop. As you warm the Arctic, more methane is released, which warms the Arctic more, which causes more methane release, and so on. So those are a few 2 minutes, I think.
Yeah.
uh,
You want to
of
throw in
the,
the wildfire connection while you're at it? How do we get
oh
more
gosh,
wildfires?
yes, of course. So yeah, and as you warm up the planet, you're drying out the land. Um, there's also I'll mention sea level rise quite briefly here. There's three reasons why sea level is rising
Yeah.
right now. One of them is we're melting ice on land,
How
so
about you?
water flows to the sea. Second reason, as you warm something up, it expands, and we're warming up the oceans, therefore they are expanding upwards. And the third reason is we're drying out the land. And so that water that we're getting through increased evaporation off of the land on our planet falls as rain into the oceans, and that's the third reason why sea level is rising. None of it's good, and my students, same as yours, Katie, particularly in a crash course on science like this, ask, when do we get to the happy part? And the answer is you get to the happy part of any problem when you do something about the problem. There's All of this is bad news. There is no good news when you look at just the science of what's happening. Um, but the good news lies in things that, like the increased adoption of renewable energy. Virtually all new energy being built out in the United States and elsewhere is renewable, 90%. And you'll see links to that in this slide deck towards the end, the happy part. And that's, so we are turning the corner on solutions. This is a great moment to be alive. But there's no question that the problem of climate change is very much still there.
So, a couple of other questions came in about resources. So, if you had great links in your slide deck, which we'll share, but are there other places that you recommend a student who'd like to learn more about specifically sort of what the scientific impacts of climate change are? I have a couple I can recommend, but what are your favorites?
I sure do. And, I think the place to start is really getting your hands around modern climate change. There's understanding what's actually happening, then talk about solutions. So the best book that will give you an introduction to modern climate change is titled Introduction to Modern Climate Change. It's Okay, it's
I
written
know
by the
it.
same professor I mentioned. That's good for you, Brian. You get an A. Um, that book written by Professor Dessler is awesome. He wrote it for his intro class at Texas A&M. So there's like 15 weeks to the semester. So there's 15 chapters to the book. You self-quiz at the end of each. It's the book I wish I'd written. Um, Dessler also has a great blog called Climate Break. I subscribe to so many of these, I can't remember all the titles. Um, but I would say start with be Brian. Start with that book. And it's a quick and easy read. You're gonna feel like you're reading high school science because it pretty much is high school level science. And then you're ready to go. Bloomberg does a very good like daily blog. Wall Street Journal, not bad. New York Times, not bad. There's dozens of others. And so, depending on what you already feel you've got under your fingertips in terms of knowledge, then you can, move on to other things, but definitely start with science. Start with Dessler.
Great. One of the ones I was going to recommend is Drawdown, which is really more related to actually how do we remove and remove carbon from the atmosphere and solve the climate crisis. Do you want to say 2 minutes about how we actually can, besides mitigating a climate, how we actually can get CO2 out of the atmosphere from a science perspective?
Yeah, it's. I wrote a case study. I've written. Uh, I discovered recently, to my horror, that 10% of the case studies on Harvard's website coming from the Haas School of Business are ones that I wrote. I never aspired to that statistic, but I've been producing a lot of case studies on the subject of climate. I have 5 that I'm working on right now together with students. And so if you go to Harvard, you'll find case studies that I've written that sort of summarize. some of this stuff. It's Harvard Business School Publishing, HBSP something, edu probably. And you'll just do a search for my name, and you'll find a bunch of case studies I've written on this. Because there are a lot. It's, Katie, we're all in the same world here. We're producing materials for business students, and I thought there'd be tons of this stuff. There isn't, so I'm creating it. And it's a small group of us who are producing these teaching materials. Short answer, though, is that if you have um, a method for putting carbon back in the ground as permanently as it had been, you've got a solution to what's called geologic sequestration. There are many, many, many other methods that take CO2 out of the air temporarily, meaning for a few decades. And those usually involve planting forests and stuff like that. And the reason that's temporary is because forests can burn and then all the CO2 is back in the atmosphere. Forests can be cut down to build shopping centers and airports and who knows what. They're not permanent. And no matter what piece of paper you have from what government that says we'll never cut this forest down, 100 years from now, that government's gone and your paper and you're gone. But that paper means nothing. So permanence is the essential ingredient to any kind of drawdown. And that means carbon capture and sequestration, but geologic sequestration. Most of the other stuff, to be honest, it isn't very durable.
Great. Well, there's so many more questions here and lots we could talk about, but we are coming close to our end of our hour. I did put a link in the chat, another resource that may be helpful to our audience. We wrote a short primer called Climate Change in Business, What Every MBA Needs to Know. Probably needs an update. It was last updated a couple years ago, but I think it'll be a good start for some of you on the call. There are some other good resources posted on the ClimateCAP website under the resources heading. And I definitely think that it is a good place to start is to really understand both all of the impacts and all of the potential solutions, which there are many, as you're thinking about where you'd like to be a change agent in the future. And the book Drawdown is a great place to look at what the potential solutions are with the sort of calculation of how much impact they can have as well as how much they will cost. So hopefully those of you on the call, there are lots more. We will, in the course of our Climate Catalyst program, we'll be talking about lots of different types of solutions and actions, mitigation, adaptation, so much more. And we will also on Thursday be doing a En-ROADS simulation, which is where you actually have a model and you can use different levers and see what kinds of outcomes you can get in terms of temperature rise in the future. So it's a really, really handy exercise to go through to kind of see where the levers at change are. Just as a last note here, let me see if I can share my screen for just a minute. I would love to thank Drew for this terrific presentation. And it's so helpful to see as a grounding for our conversations going forward to see the actual science. I'd love to thank all of you for joining us. And then I hope that you will join us for our next two sessions. Coming up today at 1:30, we are going to be talking about climate markets and the future of business with Mita Kothari from UT McCombs. And then we are going to be talking about the climate career landscape this afternoon at 2:30 Eastern time. Sorry. So hopefully you can join us for those. Take a look at our full program. Thank you again, Drew, so much for joining us today. Thank you all for being here.